The last lecture we have seen about the conditions required for a constrained optimal problem to get an optimizer. So here we will be looking at how that problem is solved. The primary advantage of model predictive control is to incorporate constraints. So we'll see how the constraints are incorporated in the optimization problem, what modifications are to be done before solving a quadratic optimization problem. So these are the input constraints. It will have a minimum value, it will have a maximum value. Each control will have a minimum and maximum, each state will have a minimum and maximum. So these are the input constraints, these are the state constraints. So this is a general form of constraint. So we will modify these constraints into this generalized form in terms of only u. So these input constraints we can write in a straightforward manner, like each uk will have a minimum maximum bound and a minimum bound. And this state constraints, we are converting it to the input constraints by using our model. So xk plus 1 is equal to xk plus buk. By using that, we will be predicting all the future states in terms of present state and the future control values. So that is how we will write this second equation. So combining this both, we will have a final form like this. So AC UK less than or equal to B0 plus BK XK. So in terms of initial state and the control values, all the variables, control variables. So this will be a fixed value and we will have a lesser than or equal to constraint. So now what we are doing is we are minimizing this. I have explained in the previous video. So how we are obtaining this and subjected to this constraint. So now this is a convex optimization problem and it has a unique solution. So the general algorithm to solve this quadratic programming is active set algorithm or interior point algorithm. So in active set, we will consider only the active constraints. A constraint is said to be active when it has an equality. So when that constraint, when it hits that constraint, when our search of the solution hits a constraint, then it's said to be active constraint. And if it is less than or equal to, it is an inactive constraint. We don't have to consider that in our optimization problem. So inactive constraints can be removed from the problem without affecting the solution. The value of the optimal value will be affected only if the constraint is active at that point. It will not be affected if the constraint is not active at that point. So what are the steps that is followed in an active set algorithm is that we will select the possible combination of equality constraints. The constraint will identify whether a constraint will be active or not, and then solve the corresponding equality constraint problem. And we will remove all the inequality constraints, and then again check the solution what we have obtained at step 2 with respect to the inequality constraints. So we will verify also that this is also being satisfied. So that is how we work in active set algorithm. But in interior point algorithm, we will have such a form like this is our cost function and this is our constraint set. What we are doing is we will write it in this form where mu is a scalar and phi is a barrier function. So the barrier function has a property that the value of the barrier function is finite when u satisfies the constraints, but when it tends to infinity as u approaches the constraint boundary. So when this value tends to increase, we will understand that we are near the constraint boundary. So the constraints will be satisfied if we minimize this. So typical barrier function we will be considering is an logarithmic function. So this solution tends to u star as mu tends to infinity. So what we are doing is we will success iteration, we will increase mu and we will try to minimize. So the solution tends to u star as mu tends to infinity. So as mu increases in successive steps, we are nearing the optimal. So that is how the optimal point is found in interior point method. So now we are finding a constraint. We are solving an example of constraint optimization problem. So these are the system matrices, and we will be taking q equal to c dash c and r is equal to 0.01. Using, there are plenty of solvers to solve this constraint optimization problem. So we'll be using quadratic programming function in MATLAB, which gives us the freedom of using any of these solvers mentioned above. So there is an option of using active set algorithm or interior point algorithm, and there are two more options by which we can solve the optimization problem. So these are the solutions that will state evolution as time progresses, and this is a control signal. So as we can see, the control signal is limited to 1 and -1. These are the constraints that I've given while implementing the problem. So the control input is constrained in these limits. So this is the advantage of MPC. So these constraints are satisfied and the optimal problem is found out. Now the most of the lecture is prepared by following this book by Burali, Bimparad and Murari, the predictive control for linear and hybrid systems, and few other points from the other books as well. So in this lecture, we have seen the finite horizon MPC, the dual mode MPC, constraint optimization, and the conditions that the optimization problem should satisfy, then quadratic programming, and an example of using quadratic programming. Thank you.